All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully, you guys are doing well on this Friday. Let me jump into it. Exciting day today. We are going to start probability. Okay, so let's actually get to that. Before, it's possible that I still don't have available times from one of the teams, but I'm not sure. So just in case, make sure I have your team's availability.
When will our advisors reach out?
One of your advisors?
When will the advisors send us an email?
Oh, it's soon, because I know they met yesterday and they mentioned that they didn't have times for everybody. And I'm not sure if I missed it or you guys just didn't send it. So that's why I'm asking now. Make sure everything's availability by today at noon. So they're setting everything up now. So I want to make sure that they can meet with everybody and when would be the best times. Okay, so we are going to be doing finite probability theory. There is a kind of probability that where you can have things like infinite sample spaces. You can have sets of infinite outcomes, things of that sort. We are not going to go anywhere near that. We are going to go with things where all possibilities can be counted in our lifetimes, and we can actually set everything up and we can know, okay, this is everything that could happen, and we just want to see if these things are happening, right? So, and we're not going to do continuous probability with calculus, none of that. Even though all of that exists, we're going to keep it very basic. We're going to keep it at finite probability. So I'm going to start, as always, from scratch. I'm going to assume that you guys know very little, anything about probability. I'm going to build up with some definitions. So how about a definition? A random experiment is a process, the outcome of which is cannot be predicted with certainty. Okay, so this is what's called a random experiment. For example, flipping a coin is a random experiment. Sure, you can know that, oh, well, it's going to be heads or tails, but you don't really know for sure, right? Or the roll of a dice, the roll of a fair dice, right? You don't really know what number it's going to land on. You know some possibilities, but until it happens, you don't really know. You can't really predict it without with any degree of certainty. Like you wouldn't bet your life that you know exactly what number the die is going to roll on. Hopefully not. So now probability seeks to measure the likelihood or chances, and this is i.e. relative frequency of various outcomes of a random experiment. So to go back to the dice roll example, remember I told you that probability was invented because of gambling. Because when you're in a gambling situation, you're in a situation where the outcome is not certain. You are gambling. So you wanted some sort of mathematics or some sort of heuristics or decision-making framework by which you could make decisions in a world where you don't know what's going to happen, right? So then how do you position yourself in the best possible way? And it started with gambling, but of course, the way I just described it can be applied in general, far more broadly. So probability is a big deal in the world at large, statistics and probability. It's a very important branch of applied mathematics, and it is everywhere. What can I say? It's everywhere, especially now. I mean, one thing that you guys will be able to appreciate is the thing about these AI and machine learning and all that stuff, and Siri and Cortana and whatever. And you should really know that they're only possible because of probability. Yeah, what AI and machine learning are, it's kind of like applied probability, statistics, linear algebra, calculus, and a little bit of computer science. That's what makes an artificial intelligence, really. So probability is super important, and we live in a world where we can't always predict everything, but we'd want to know what are the chances of something that's going to happen, right? What are the chances that if Siri tells you a random joke, you'll find it funny? Say, Siri, tell me a joke, and she picks a random joke. What are the chances that you are going to find it funny, right? Apple would be interested to know that that probability is going to be high, because then you keep using it, and then they have you now, and then they trick you into getting an iPad. And let's move on. Definition. Okay, so the sample space of a random experiment so this is a very important definition. It's called the sample space. Is the set, I want you to appreciate that it is a set that we're talking about, of all possible outcomes of the experiment. Okay. Another definition, the elements of the sample space are called sample points. Here's another definition. An event is a subset of the sample space. Okay. So when you list all possible things that can happen, you say you've listed, you've put all the sample points into a set. And if you take a subset of that set, you create what's called an event, right? So an event is really just a subset of the set of possibilities, right? And sometimes we're going to want to be able to measure that. Here's a definition. Sample points are said to be equally likely someone's trying to get in here. If they all have the same chance, and I'm going to define that word more precisely, of occurring. So for example, when I flip a coin, we can say heads or tails, they're both equally likely. They both have the same chance of occurring. It's not like one is more likely than the other. You wouldn't assume that, you know what, I'm going to get heads 90% of the time and tails only 10% of the time. It wouldn't be an assumption you would make. It would be a set of equally likely outcomes, we call it. Now let's, notes here. In this course, we always will consider the sample space to be a finite set. It doesn't have to be in general, but for this course, it will be. So it's always going to be a finite set. All right. So now let S be a sample space with equally likely sample points. Another common notation is uppercase omega. Very common to call a sample space uppercase omega for whatever reason. So yeah, and let A subset of S be an event. Okay, so now definition. The probability of A which is denoted P of A or boldface P of A, but I'll use the first one because I'm lazy. Then what is that is given by probability of A equals the size of A divided by the size of the sample space. Right? And this is what we also call the chance of A, the likelihood of A, that's AKA. Okay, so that's how we define probability. Find a sample space of equally likely outcomes. Take a subset of those outcomes that you're interested in, measure the size of the set, the subset, and divide it by the size of the sample space, right? Obviously, counting is going to be important for these. Counting. Because you're measuring the size of things, you're going to be counting them. Yeah, so let's do a very simple example just to get you guys on board with this, what's going on. So let's say you flip a fair coin. By the way, a coin is a very interesting thing. I don't think in reality you can actually make an unfair coin, but maybe someone can prove me wrong there. I feel like you can't. So you can make an unfair die for sure. You can make a six-sided die where like one side would always come up a lot more than the other sides. But to make a coin where like heads outweighs tails in reality, I don't think it can be done. Yeah? It's hard. Like they usually do it by weighting, but coins are weird. Let's see. Okay, so you flip a fair coin, and I ask you, what is the probability of getting heads? And that's the side of the coin with the guy's face on it, right? So what you would do here is you'd realize that here S is the set, well, H or T, right? Can be heads or tails. And this implies that the size of S is 2. Then also A, the event we care about, would be H. And you'd say that the size of that is 1. This means the probability of A is the probability of getting heads is going to be the size of A divided by the size of S, and it's going to be 1/2, right? So we can say it's a half. There are only 2 possibilities. This represents all possibilities. The possibilities are equally likely, and the one that I care about is getting an H. So I can find the size of the set that has what I want, the H, find the size of the set that gives me the total possibilities. This set is called the sample space, and I divide the size of the set I care about by the size of the entire space, right? And that gives us a probability. So this leads to a basic process for finding probabilities. And we'll come up with rules or formulas to skip some of these steps sometimes, but this is essentially, you're always kind of doing this in the background. Right? But if you're ever lost, you're in a situation where you don't really know what's going on and you want to tread carefully, this is how you're going to build up to finding a probability, right? There are certain situations that we understand very well that we can come up with formulas to cover those situations, where on the back end, we already considered all this and we came up with a formula that takes all this into account. But for the most part, this is what finding a probability comes down to. 1, you are going to create the sample space. There's always a sample space in the background. The sample space is kind of like your universal set, right? It's always assumed to be there. It's always there. Even if you never really mention it, it's always assumed to be there. Here, you need to be creative. It is probably, it's step 1, but it's probably the hardest step. Right? Just kind of knowing how to visualize the situation that you're looking on. How do I want to set up the set of all possibilities? Do I want to count sets? Do I want to count tuples? Do I want to count words? Do I want to count phrases? How am I going to construct a set? Right? A set is a very general thing, a collection of objects. What kind of objects would I want to put into this set? How do I know that this set of objects covers all possible cases? Right? To actually come up with that set can be the real challenge. It turns out, though, once you've done that, it tends to be easy to do the rest, easier. Find the event A in S that you care about. Three, you're going to find the size of S and the size of A. And then 4, you have that formula. The probability of A is the size of A over the size of S. And that's it. Seems like a very simple process. Oh, just 4 steps. Oh, you find this set and then you find that set and then you just Measure them. Okay, we will get to it. Now, probability, like all of mathematics, is based on axioms. Axioms are things that we assume to be true without proof, right? Which comes as a surprise to some people. That there are a lot of people who feel like mathematics is built into the universe, was given to us by the gods, and we're slowly discovering. It's not true. Math is a bunch of rules that a bunch of dudes made up a long time ago that were like, you know what, let's just believe this and not ask any questions about it, and let's build from that logically. That's what math is. It's really like a big game. It's like a chess game. So when someone says, yo, I'm just not good at math, it's kind of like they're saying, I can never be good at chess, which in some sense, you might not be Magnus Carlsen, you might not be the greatest chess player in the world, but you can learn chess. You know what I mean? It's just a bunch of rules that you follow just because, right? So these are called axioms. These are rules that everyone just says, we will accept this as truth, not going to ask any questions, and we're going to move on from there. And the idea is, usually these rules that we accept as truth come from how we understand the world, how we understand the universe, how we understand anything. So we're like, okay, I have one apple and then I have another apple and I have two apples. And oh, let's apply this concept in general, the concept of number. Let's create some axioms that behave like that. And the reason why math is so useful in real life is because of that. The basis of math is built from an understanding of our universe. So once we build from that logically, it seems to describe our universe very well. So let's talk about the axioms of probability because they're very important. And the axioms of probability, they're helped by the axioms of set theory. So how we can deal with probability, we can use set theory because we're setting things up in terms of sets. But as far as probability is concerned, there are really only three things that we assume without proof. Everything else in probability, we can prove it. We know why it happens, why it has to be true. We can justify it. Here are some things that we can't justify. For any event A, probability of A is a real number such that it falls between 0 and 1. Probability will always be between 0 and 1. It will never be outside of the range of 0 and 1. If you tell me on a test the probability is 1.3, I will know you have no idea what you're talking about. That is impossible. That's like telling me the knight can move like a queen. No, it cannot. That's not in the rules. The knight moves in an L. What are you talking about, right? Someone says that to you, oh, the knight can move along the diagonal all the way across the board. You'll know that that person knows nothing about chess. You know nothing, Jon Snow, right? So probability is always between 0 and 1. If you give me a probability that's not between 0 and 1, and you don't, so this is kind of a half thing. So if you give me a probability that's not between 0 and 1, and you say, oh, the probability is 1.7, and you just move on with your life, I'm going to punish you very heavily for this. Like I would take off so many points, probably all the points for that problem. But if you tell me, okay, I'm getting the probability is 1.7, I know this is wrong, but I don't know where my mistake is, then I'm like, okay, at least they know, at least they know they're wrong. They know that something is off. I'll be a bit more lenient there. But in general, probability is between 0 and 1. It is a very important fact. It will never be outside this range, right? There is either going to be a 0% chance of something happening or anything up to 100% chance of something happening. You cannot go beyond that. By the way, this matches the definition in the sense that we now know so if I were to find the probability of S, by the definition, this would be the size of S over the size of S, which is 1. Okay? So the probability that something in the sample space is going to happen is 1. It will occur because this is the set of all possibilities, and possibilities have to happen, right? One of the possibilities have to happen, right? We have a universe where stuff is happening all the time. Then we can also know that the probability of the empty set is the size of the empty set over the size of S. It's going to be 0 over the size of S. This will be 0. The probability of nothing happening is 0. I flip a coin. What is the probability that I won't get heads or tails? Like nothing is going to happen. Well, there's 0 probability of that happening, right? So we know this. The probability of the entire sample space is 1. The probability of the empty set is 0. Okay, so we can know that from that axiom. 2. The probability of the sample space is 1. That is going to be, so we always assume that when we create a sample space, something in the sample space has to occur, right? Something is going to happen. So the probability that some event in the sample space will occur is 1. Okay, 3. If A1, A2, all the way up to AN are disjoint sets. I defined disjoint for you last time. Recall that disjoint means that the sets have an empty intersection, right? So we did that down, I think, all the way at the bottom, right? A and B are disjoint if their intersection is the empty set. So they're completely separate is what I'm saying. So these subsets have nothing in common. So let's say these guys are all disjoint sets. Then disjoint, let me make it a little bit more specific. Disjoint subsets in a sample space. So if I already have a sample space, I know all possibilities, I take a bunch of subsets from the set of all possibilities in such a way that none of them overlap. Then the probability of A1 union A2 union ... union AN is the probability of A1 plus the probability of A2 plus ... the probability of AN. To find that one event or another or a third or a fourth, etc., will occur within a sample space, if those guys are disjoint, it's just the sum of the probabilities. And I really should underline this because the OR formula for probability is not this in general. This only happens if they are disjoint, right? So OR is not always adding. OR is only adding if there's no overlap. So that's it. That's it. That's all we assume for probability. The thing with axioms is, yes, we don't assume that any justification for them, but we have to make them as minimal as possible. We don't want to assume too much because it turns out human intuition can lead you astray very, very quickly. So you want to keep your axioms to a bare minimum. And for probability, that's the bare minimum. Those three things are the only things we assume without any proof. Everything else we can justify. So in fact, let's justify something else. The general formula for an OR, at least with two sets. we have what's called the law of disjunction. Basically, that says if A, B are events in a sample space, then the probability of A or B is the probability of A plus the probability of B minus the probability of A intersect B. That's called the law of disjunction. This is true in general, whether they are disjoint or not. And of course, if they're disjoint, you will know that the probability of the intersection would be 0 because it would be the empty set. And so you just get the sum of the probabilities, right? So in the case of disjoint, you get back the third axiom. But if they're not disjoint, you have to worry about where the overlaps happen, and you have to kind of add or subtract them. You do this according to the inclusion-exclusion principle, which I mentioned before. In fact, why? Well, the probability of A or B is the size of A or B over the size of S. This is by definition. Okay, but how do we measure the size of A or B? Well, we know that that was the size of A plus the size of B minus the size of A intersect B. And that is by inclusion-exclusion. But we know how fractions work. I can split this up across the denominator. And then each of these, by definition, the first one is the size of A over the size of S. By definition, that is the probability of A. Second one is the size of B over the size of S. By definition, that's the probability of B. Minus the third one is the size of the intersection over the size of S. By definition, that's the probability of the intersection. Right? So once I assume the definition of probability, I can figure out that the probability of an OR is this guy. Now, if A and B are disjoint, then I take away this last part, and then the probability just becomes the sum of the two probabilities, which falls in line with the third axiom. Also recall, so that's that. Recall that we have the universal set is the same as a set union its complement. We did that a while back. In probability, we always consider the universal set So that means that our S can be thought of as any event union the complement of that event. And A and A complement are disjoint, right? They have no overlap. By definition, the complement is everything that's not in A, right? So there's not going to be anything that is in both A and A complement, right? A is a subset of the universal set. The complement of that set is everything in the universal set that is not in that set. So these guys are disjoint. So this means the probability of S is going to be the probability of A union A complement, and this is going to be equal to the probability of A plus the probability of A complement, since disjoint. or let me put by axiom 3. And this is 1, and this is by axiom 1, axiom 2, and maybe I should. Okay, and so we obtain that 1 is always equal to the probability of A plus the probability of the complement of A. And in fact, we can say that the probability of an event is 1 minus the probability that that event does not occur. This is going to be very important. This is called the complement probability formula. Sometimes it's easier to know when something will not happen as opposed to when it will happen. And so what you can do is if you're interested in something happening, you can always look at, well, is it not happening easier to conceptualize? And if so, what you would do is you just do the opposite. Let's see what are the probability of it not happening. And then 1 minus that probability will give me the probability of the original thing happening, right? So we can have that. That's called the complement probability. I.e., the probability of what you want is 1 minus the probability of what you don't want. And this is true in general. It's always true. Okay. So this is always an option you will have on the table, right? Sometimes you care about something specific, but it's hard to kind of wrap your head around that thing, or just harder than it would be to wrap your head around the opposite of that thing. And so you focus on the opposite, right? So the complement formula is useful when counting the events in the complement is easier than counting the events. Events in A. Maybe I should give you an example. You flip a fair coin 3 times. What is the probability you get at least 1 heads? Okay. So let's say that is the probability that you care about. Now, of course, recall or note, at least means greater than or equal to. At most means less than or equal to. So the probability of at least, I don't want to be writing this down all the time. So let A be the event we get at least one H. And notice that the probability of A is going to be the probability that we get one H or two H's or three H's, right? Now, how many ways can we do that, right? How many ways can we get this? Well, that's going to be the probability of one H plus the probability of two H's plus the probability of three H's, right? Because these would be disjoint, right? I can't have flipped it three times and I both got one head and at the same time I got two heads, right? Not possible, right? So these are both disjoint. But now you have to worry about, well, how many ways can I get one head? Well, it can happen on the first or the second and the third. How many ways can I get two heads? Well, it can happen on the first and the second, or the first and the third, or the second and the third. And right, so notice that it's going to be, there are many situations in each. Well, there's only one situation in that one, but in general, many situations in each. Now, note, a complement would be we do not get at least one head. Tell me another way to think about that. What would it mean that we don't get at least one head? What would have to happen?
That we kept getting tails.
You get all tails. How many ways can that happen?
One way.
There's one way. Right? That's the opposite is super easy to count. There's only one way that I could not have what I just asked about. So now you can go in. All right. To figure out what I want, I'd have to break it up into cases. Then I'd have to make sure I count all possibilities, all possible rearrangements. However, what I don't want is TTT. And that can happen in one way, right? So now you can go in and you can like, okay, let S equals the set of all possible triples, right? So X, Y, Z, such that X equals H or T, Y equals H or T, Z equals H or T. Right, so that's my sample space. So this is just like heads, 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 or heads, heads, tails, or da-da-da, all the way up to tails, tails, tails. And what we want, let A equals the set X, Y, Z such that at least one of X, Y, Z equals H. Right? So this would be the set like HTT would be in there, HHH would be in there, HHT would be in there. At least one H must show up in my coordinates. And so now notice then that your A complement would actually just be TTT and nothing else in that, right? So now you'll notice that the size of S, well, what is S? I just thought of it as a bunch of triples, right? This is the number of three tuples with 2 choices per entry. We know what that is. This is 2 to the 3 by the multiplication rule. So the size of S is 8. Now, the size of A is somewhat annoying to figure out. But the size of A complement, well, that's 1. It's easy to see that that's 1. So then I can say, well, the probability of A is just going to be 1 minus the probability of A complement. The probability of A complement is the size of A complement divided by the size of S. And that's that. So the probability of at least 1 head is 7/8. Right? Now, again, this is a very simple example. I wouldn't expect you to have to go through all this for like a coin flip, but it shows you the process of how you want to think through a probability problem. You want to set up my set of all possibilities. Okay, so this is all possibilities. Okay, what are the things that I want? You create a subset of the set of all possibilities. So I go through and I create the subset where there's at least 1 H in the coordinates, right? Sometimes that's going to kind of be annoying because you're going to be like, okay, well, where are the H's going to go? And you have to count all of them. So sometimes you consider the opposite, right? What would it mean to not have at least 1 H in the coordinates? Well, it would have to have all T's, and there's only one way for that to happen. And so we can actually get to the probability of what we want by going to the probability of something we don't want. And for now, that's where I want to stop, but I will leave you guys with some examples for next time. So not very crazy examples at this point. It is going to be on the level of some of the easier probability teasers that I gave you guys like a week ago. But be sure to try them for next time. I will say that this one is going to be interesting, and it's going to lead us to another concept in probability. So try these for next time. So at the moment, we have all the basics that we would need. Of course, we're going to develop probability a little bit more, but for now, you should be able to do almost any problem with what I've told you. The only thing is that sometimes it can be easier to do what I told you. And so I'm going to, after this point, sort of develop some rules that allow you to take shortcuts, right? So maybe you don't have to actually know what the sample space is. Maybe there's a shortcut for knowing how many things are in the sample space without actually constructing the set, things like that. So yeah, I think we'll stop there. So thank you for your time and attention. I will head into the other class now. Make sure that your group actually sent me your availability. If not, send me in the next couple hours or so. All right. That being said, I will see you guys. Have a good weekend. I'll see you in the next one. Ciao.